Welcome learners. In today's lecture, we are going to look into another powerful technique which helps us in solving the complex electric circuits or which helps us in analyzing any electric circuit. The topic is called source transformation. So before this technique, we already know that we can solve any circuit by either using the node voltage method. We can solve it using the mesh current analysis. We can also simplify any complex circuit if we have bridge configurations. By bridge configurations, I mean the delta to Y and Y to delta conversions. This is also known as pi to T and T to pi conversions. Apart from this, we also know the resistance simplification techniques. Those simplifications being that we find the R equivalent, whether it is in series configuration or parallel configuration. So these powerful techniques are available to us, but we want to add more to our knowledge base, and we now look into another technique which is called source transformation. And the idea behind using the source transformation is what to do if we have multiple sources, independent or dependent sources available in a circuit. So we can have dependent or independent voltage source, whether it is voltage controlled or current controlled, or we can have independent and dependent current control sources. So how to deal with those complex circuits, or how we can basically simplify those circuits for our analysis. So what is basically source transformation? So source transformation is whenever we have a voltage source, dependent or independent. So whenever we have a voltage source in series with a resistor, and it should be a single resistor, not multiple. If we have multiple resistors, we can add them to be a single resistor. So whenever we have a voltage source in series with a resistor, we replace it with a current source in parallel to the same resistor. What does it mean? So for example, if I have a voltage source, or if I have any circuit where this configuration is appearing, that I have a voltage source V of S and I have a single resistor next to it in series, let me call this R1, and these are the terminals of the circuit A and B. So what I can do is I can transform this source into a similar source of current nature, and the same resistor now is in parallel with this current source. So this is my current source IS, and the same resistor R1, which was in series with the voltage source, now becomes in parallel with the same with the current source and having the same terminals A and B. So this is what it means by doing the source transformation. And if you look closely, I have used this indication or double direction symbol, which means that if I find any current source in this configuration in parallel, I can also transform it back to the voltage source. So if I have a voltage source in series with a series resistor, I can transform it to a current source and vice versa. And this is basically source transformation is happening. Now the question arises that how can we be sure that this transformation is accepting the electrical laws, or how is this basically happening? So in order to understand this, that how this can happen, this transformation, we basically look at the principle of equivalence at the terminals. Equivalence at the terminals. So what does it mean, the equivalence at the terminals? So it means that whenever we have a load resistor or any load, we call it normally RL, connected at the terminals of the circuit, connected at the terminals of any circuit, any electric circuit, let's put it in a precise manner, we will observe that the voltage drop and the flow of current will be the same, will be the same. So this means that both circuits will behaving equivalently at the terminal characteristics. So what does it mean? Let us understand it from this image. So let us say I have this figure A, where I have an independent voltage source V of S and I have a resistor connected in series, which is R. Now let us say that at the terminals of this circuit, at terminal A and B, I connect any load. I am calling it RL, and we want to see, in order to see that this conversion from voltage to current is accepting the electrical norms, so we basically look into the flow of current through this load RL. Okay, we know from the source transformation that if I want to convert this voltage source into a current source, so its behavior or its configuration will look like an independent current source I of S, and the same resistor R is going to appear parallel to the source. Now let us consider that the load is connected to the terminals A and B of the image B, and I want to verify that these conversions are possible based on the equivalence terminal principle, which is this one. So in order to verify this, let us take one example and see the flow of current IL through both the loads. So if I look at this IL, and let us see how can I find this IL. So for the figure A, we can see that it's simple Ohm's law, that the load current is basically the ratio of the voltage and the sum of resistors. So this is giving the value of IL equals to Vs by R plus RL. And similarly, if I want to find for the second image B the load current IL, I can apply the current divider rule, and the current divider rule is basically giving me this equation where the unknown current IL depends upon the ratio of this resistor multiplied with the source current divided by the sum of resistors Rn plus RL. Now if I focus on this point, this is nothing but a voltage source divided by R plus RL. So in general, I can say that this is again Ohm's law, and it is following Vs by R, similar to this Ohm's law over here, which is V by Rs. So in generically, I can say that both the circuits are following the Ohm law, and the flow of current through both the load resistors is Vs by R. This means that the equivalence principle holds, and I am able to do these conversions either from voltage source to current source or from current source to voltage source. So this is how we prove from the equivalence terminal behavior that this transformation is possible. Now let us see and put this scenario to a simple example and understand that how these conversions take place. So for example, I have a voltage source. So this is a very generic example. We are going to look into more examples as well. And this is terminal A, this is terminal B, this is 50 ohm of resistance, and let us say this is 10 volt. Now if I want to convert this configuration into a current source, or I want to transform this, so I can write as voltage source is represented by a current source, and the same resistor is now applied in parallel to the current source with the terminals being A and B. And what is going to be the value of the current? So again, following the Ohm's law, it is going to be V by R, where in this case the voltage was 10 volts, resistor being 50 ohm, so I get 0.2 amps of current. So this is what I am getting. Similarly, if I had this current source and I wanted to move back So the configuration will be such as it is shown here, and the voltage then comes out to be V equals to IR, which is going to be 0.2 multiplied by 50, and it again comes out to be 10 volts. So this is a very straightforward example of how we can do the transformation between a voltage source to a current source, given that the sources follow the rule that the voltage source is connected to a resistor in series and the current is following the connection with a parallel resistor across it. Now, before we proceed further to some more examples, there are certain rules that we want to follow when working with source transformations, and those rules are, let us say, rule number 1. That rule is, what happens to the voltage source, or if you have multiple sources, let's say we start with voltage sources in series, then rule number 2 is, what about current sources in parallel? And let us first solve this, and then we are going to look into the other two rules as well. So there are 4 rules that we follow when solving the problems or analyzing the circuits related to source transformation. So let us say if I have this configuration, I have a voltage source, all are connected to terminals A and B. This is plus minus, this is plus minus, this is, let's say, 6 volts, this is 3 volts. So how I can represent this kind of a voltage? The second scenario can be if I have something like this, a negative with a positive. Again, I can say a negative with a positive, and then I have terminals A and B. So how I can represent this kind of voltage source? Let's say this is 4 volts and 5 volts. What is going to be the behavior over here? Similarly, let us say if I have a plus voltage source with a negative followed by another negative source with a positive. So what is going to be the behavior now? Plus minus minus plus, let us say this is 9 volts and 6 volts. So what voltage can I take for this scenario? So let us solve this one first. So whenever we see the voltages connected in a single branch or in a series configuration, we have to look at its polarity, and especially the ones that are back to back or next to each other. For example, in this case, we had polarity of plus minus followed by plus minus. So look at the polarity over here. These are of different polarities. So when we have different polarities followed by each other, we basically sum them together. So the output will be a single voltage source, terminal A, B, plus minus, and the value will be 9 volt. So when two voltage sources appear in series and the polarities are different, we basically add them together. Similarly, in this example, we have again different polarities, plus and minus, so we will have a single voltage source. Let's say this is terminal B and A, and this will be 9 volts again. What about if we have same polarities? So whenever we have same polarities, we basically differentiate, take the difference of them, or we subtract them. So the output of this will come a single voltage source with 3 volts of value at terminals A and B. So remember that whenever we have different polarities back to back, we basically take the sum and give a single voltage source, and whenever we have same polarities, we basically take the difference of it to get a single voltage source as shown here. Now let's talk about the current sources. So we learned about the voltage sources rule. Now what about the current sources? So for the current sources, let us say we have this kind of possibility, that I have a current source in upward direction followed by another current source in the upward direction, and they both are connected to terminals A and B. Let me call this 2 amps and let me call this 3 amps. Again, let us take another scenario where I have currents in the opposite direction, or basically the sources are in the opposite direction, and again terminal A and terminal B. So what is going to be the output of these two scenarios? So whenever we have two current sources, let us say this is 6 amps and 2 amps. Okay, so the first scenario is whenever we have different currents, or let's say these two currents are in the same upward direction, so I can sum them together in a single current source, and I'm going to add them, or I'm going to sum them. So the output will be a 5 amps of source connected to the terminals A and B. Similarly, if I have current source which are in opposite direction, so I'm going to subtract them or take a difference of these two currents. Again, the terminal behavior remains the same, but the direction of current will be, so this will come as 4 amps, and the direction of the current will be of the higher value. So 6 amps direction was in the upward way, so the output will also be in the upward direction. So this is how the current source is going to behave when you have multiple current sources in parallel to each other or in multiple branches. So this was the second rule. Now let us come to the third rule, and it is an obvious one, that what happens if we have, so the third rule is what happens if we have two sources together in a branch. What does it mean? Let us say if I have a voltage source followed by a current source like this, again connected to its terminal. So this is, let's say, V of S, and this is I of S. What is going to be the output? Which is going to take precedence over the other? Similarly, I can also have this configuration that I have a current source and I also have a voltage source connected in parallel to each other. So this is my V of S, this is my I of S. Again, this is terminal A, etc. So where is going to take the precedence? So for these kind of situations, we basically rely on our series and parallel rules for voltages and currents. We know that if we have a series branch, the current remains the same and the voltage drop appears or voltage is different. So for this scenario, we are going to consider that our source will be of the electric current source I of S at terminals A and B, and we are going to ignore the voltage source. Remember that whenever we are doing the practical analysis, the sources cannot be ignored. As I talked about the voltage sources, they are going to be there, but when we are doing the theoretical analysis, we consider that the current source is going to dominate in our configuration. And what happens if we have these sources in parallel? So again, voltage remains the same in parallel, so the output of this, or the dominance, will be of the voltage source when we are doing the source transformation analysis. So this was the third rule. And the final rule for solving source transformations is rule number 4, which is, now what happens if I have a voltage source and we know that the resistor has to be in series. So for the voltage source transformation, in order to transform this voltage to current, this is what we just discussed about source transformation. So this is, let's say, R1, and this is R1, this is current. Now what happens that if we have this configuration and we are interested in the transformation, but we see that the voltage source has a resistor in parallel next to it, let me call this RA. Similarly, for the current source, before R1 I find something in series, which is, let us call this RA. So when this kind of configuration appears, what should we do? So what we do is we normally ignore this branch or the resistor element present over here. So what I can do is, for transformation from voltage to current source, if this configuration is appearing, I'm going to ignore this resistor. The branch will remain there, so we can say that this resistor gets ignored and we only have a short circuit wire over here. So this is like this, and the short circuit wire, we know that voltage is basically nothing, it is going to be 0. Similarly, for the current case, whenever the resistor appears before the parallel resistor R1, so we are going to ignore this resistor and consider to be a short circuit. So the sorry for that, I'll redraw this. So what happens is, this is what we had. Okay, so now if any resistor comes before the parallel resistor RA, we are going to ignore this resistor and say that it is not here. So we consider this line to be a short circuited line where the current will easily flow, and we'll solve the circuit as it normally is. So these are the 4 conditions that we have to know, and if they appear, then how we are going to deal with this kind of analysis or these kind of sources. So now let us look at few examples to better grasp the source transformation related problems or analysis. So let us take a look at one of the example and see how we can solve that. Okay, so let me divide the screen and see if we can solve this. So example number 1, let us say we have this circuit. So I have a 4 ohm resistor, then I have a current source of 3 amps. So this is a 4 ohm resistor, this is a 3 amp current, and then I have a 2 ohm resistor followed by 8 ohm resistor. This is 2 ohm, this is 8 ohm. Then I have a 3 ohm resistor followed by a 12 volt voltage source. So 3 ohm and 12 volt voltage source. I have been asked for this question, find the output voltage or find V out, where V out is basically appearing across this 8 ohm resistor. So this is the voltage drop that I need to find, V out, which is appearing across the 8 ohm resistor. So let us see how we can go about solving this process. So the source transformation says that whenever I see a current source in parallel or a voltage source in series with a resistor, I can transform this. So if I look at my circuit and start from the left side, I see that this 4 and 3 ohm are basically following the rule of the current. So I can transform this into a voltage source. So I can write it as, this is my voltage source followed by the same resistor, but this will now come in series, and then I have my circuit as it was. So this will become 4 ohm, this will become negative positive because the flow of current is like this, and the voltage is going to be V equals to IR. So the source voltage comes out to be 4 into 3, 12 volts. So this is the voltage that I got, and the circuit remains as it is. So this is 2 ohm followed by 8 ohm. Okay, so this is 2 ohm, this is 8 ohm, this is the voltage I need to find. And what about this side? If we come to the right side, I can see that this voltage is now in series with the resistor, so I can transform this into the current source. So this resistor will now become a parallel one. So this will become 3 ohm, and this side will be a current source, the voltage source replaced. So I equals to V by R, and it comes out to be 4 amps. So this is the current that I got. So I did the transformation on the left and right side of the 8 ohm resistor. Now what is the next step that I can do? I can see that this is again in series, so I can add them together, and again it is appearing with the voltage source, so I can transform this into a current source. So this now becomes, so now the circuit becomes, again I'll take a current source in the downward direction, and I will transform this 6 into parallel. So this becomes 6, and this time IS becomes 2 amps, and the remaining circuit is as it is. So now followed by 8 ohm, where I need to find the unknown voltage V out, and then it is followed by the 3 ohm, and then I have the current source of 4 amps. Now this is the circuit which I have reached to. Now if I look back again to the circuit, what else can I do in terms of simplification? So I look at the circuit and I feel that this 6 ohm resistor is in parallel with the 3 ohm resistor, and I also note that the current source 2 amps is also in parallel with this 4 amps. Since there is no other element in this branch, so I can take this configuration because all the elements are connected in parallel to each other, which means if I first solve this and this as R equivalent, I should get the value of 3 multiplied by 6 divided by 3 plus 6. So this should be equal to 2 ohms. So this is the R equivalent which I am getting. And what about the current sources? Since the current sources 4 amps and 2 amps are in the opposite direction, and based on the rule which we saw, that if I have a current in the downward direction and the other current is in the upward direction and they both are parallel to each other, the output will be a single direction. Obviously the precedence of the arrow will be for the higher value. So this was 4 amps, this was 2 amps, so the current source will be a difference of 2 amps. So this is what I am getting: equivalent resistance of 2 ohm and current of 2 amps. So let me redraw this circuit with the new values. So I will have now the equivalent resistance R equivalent is basically 2 ohm, followed by the current source of 2 amps, and then I have our original 8 ohm as it is, where I need to find the unknown voltage V out. So this is now my simplified circuit is looking. Now if I again look into this, I have the current source again in parallel with the R equivalent. So this means I can further change this into a voltage source. So this will be a voltage source followed by the same R equivalent in series, and then I have the 8 ohm appearing as it is. So this is the 2 ohm, and this will be the voltage source where V equals to IR, and voltage comes out to be 4 volts. Now the circuit becomes very easy to solve. It is straightforward because I need to find this voltage, and I have a voltage source and the series resistor, so I can apply the voltage divider rule, VDR, which says if you want to find the unknown voltage, you take its resistance, multiply it with the voltage source, and then you divide it by the sum of resistors. So this comes out to be 8 into 4 divided by 10, and this comes out to be 3.2 volts. So this is the output voltage which we required, and we did this by using the source transformation technique. Okay, now let us take a look at another example and see what else or what other possibilities we can have when solving with the source transformation related questions. So this is another example that we can solve. Let us say example number 2. Now in this example, we have been given a circuit that is 6 ohm over here, followed by a current of 5 amps. Then I have another resistor of 3 amps, and now I have a voltage source over here of 5 volts. Then it is connected to a 7 ohm resistor, followed by another current source of 3 amps, and then followed by 2 resistors of 4 ohm and 1 ohm. And I have been asked, let us say, to find the current I, where the current is basically flowing through the 7 ohm resistor, which is over here. Okay, so this is the unknown current that we need to figure out. So let us first analyze the circuit and see which elements can be changed and which can be combined together or which can be simplified. If I look at the circuit, I can see immediately that this 6 ohm resistor is in parallel with the 3 ohm resistor, and I can also see that 1 ohm is in series with the 4 ohm onto the right of the 7 ohm branch. So first I'm going to figure out the R equivalent from these two, which comes out to be 6 into 3 divided by 6 plus 3, and this comes out to be 2 ohm. So this is the first thing. The second is when these two are added together, I get the resistance of 5 ohm, which will be in parallel to the 3 ohm. So let me redraw this circuit with the updated values. So the current source remains as it is, 5 amps. I have now a parallel of 2 ohm equivalent, so this is the 5 amps, followed by the voltage source, which is again a 5 volt battery, followed by the 7 ohm, where we have the current, and here this current remains the same as 3 amps. And now we have a series of resistor of 5 ohm in parallel to the 3 ohm. Now if I look back at the circuit, what else or what simplifications I can do? Again, I can immediately see that this 5 ohm and 3 amps are can be easily transformed into voltage source, and similarly this 5 amp and 2 ohm can be transformed into a voltage source. So let me transform this into a voltage source. So here it will become as a voltage source. The 2 ohm will be now in series, then followed by the 5 volt power supply. This will be 2 ohm. The voltage becomes V equals to IR, where voltage is 15 volts. Then I have the 7 ohm resistance, where the unknown current needs to be figured out, and then this becomes the voltage source of again 15 volts, followed by the resistor in series, which is 5 ohm. So this is now the simplified circuit which I have. Now again, looking into this, there is one step that I can do. Did I miss? Yes, okay. This is sorry, V equals to IR. This is going to be 10 volts. Okay. Now what we can do now here is further simplify the circuit, in the sense that if you look, we are now using the rules of source transformation, where this voltage source is in series with this voltage source. So I can combine it to a voltage source of single voltage connected with the 2 ohm resistor. So now this becomes as a 15 voltage, because again look at the polarity, negative plus followed by negative plus. So we will add the voltages. So this becomes 15 volts, and the circuit is now like this. So this is 15 volts, this is the 7 ohm, I have 5 ohm, and then I have the voltage source of 15 volts, and this is the 5 ohm. Now this is the circuit which I have now. Now what can be done? Again, this can be transformed into a current source, and this can be transformed into a current source. So let us do the transformation. So the transformation will give us the circuit as a current source. So this will be a current source, followed by the same resistor, but now it is in parallel to it. So this is the 2 ohm. I comes out to be V by R, which is 15 divided by 2. Let us say it is 7.5 amps. Then followed by the unknown current in the 7 ohm resistor, and then followed by the 5 ohm in parallel connected to the current source, which we transform, and that is 3 amps. So now this is the circuit. Again, things are getting quite simplified now. I can directly see that this is the unknown current I need to find, but I know that this 2 ohm and this 2 ohm are in parallel. Similarly, this current source and this current source can be added together. So my circuit can be further simplified to, so the 7 ohms remains as it is, followed by an equivalent resistance of 10 divided by 7, and the current source comes out to be 10.5 amps, because I have added 3 plus 7.5, so it comes out to be 10.5, and when you take the R equivalent of 2 ohm and 5 ohm, you get 10.7. So let me write this as R equivalent, and the unknown current remains as this. Now it is very simple. I can just apply the current division rule to find the unknown current, which is I. So it comes out to be 10 divided by 7 multiplied by the source current 10.5 amps divided by 10 divided by 7, the sum of resistors plus 7, and the output current comes out to be 1.78 amps. And this is how we solve the unknowns, or figure out the unknown current, using the source transformation technique. So let me give you a few more examples as a practice session where you can figure out how to solve these, and I'll give you the answer to that. Let us say some practice problem. Let's say this is practice problem 1. So let us say you have this circuit of 6 volts source connected to a 4 ohm resistor, and then you have 6 ohm connected to 20 ohm, then you have this connected to 5 ohm, and then you have a voltage source. So this is a 40 volt source, this is 5 ohm, this is 20 ohm, this is 6 ohm, this is 30, this is 10, this is 4, and this is a 6 volt source. In this question, find the power at the 6 volt source, and you have to use source transformation techniques. So this is one question that you can practice. Another one you can try yourself. Okay, I'll leave you with the answers as well, so you can verify. The solution to this comes out to be that the power at the 6 voltage source is going to be 4.95 watts, which means this power is getting consumed or absorbed. So this is the power. Another question that you can practice to have a better understanding of this is where we use the fourth rule, where you have the unwanted resistors and you can ignore it. For example, you have a voltage source, and this is one resistor, this is another resistor, followed by a current source and a resistor. Then you have another resistor followed by series resistors. So let us say this is 15 ohm, 5 ohm, 100 ohm. This is output we want to find. This is 8 amps followed by a 10 ohm resistor followed by 25, 125 ohm, and this is a 250 volts battery source. And you need to, for this question, you can try to figure out what is the output, and you can use rule number 4 specifically for this kind of a problem. The answer that you should get after solving this, that V out comes out to be 20 volts. So have a look at these problems, practice problems, these two practice problems, and try for yourself then how to solve these source transformation techniques. And that's it for today's lecture. Thank you very much.